in the previous class we have discussed about the temperature indicator, how to design a temperature indicator using IC sensor. So, there we had used LM335 as a temperature sensor, and then using that we had discussed about how to design the temperature indicator. So, if you go back to the old circuit, so that is how the old circuit looks like. So, the old circuit what we had discussed in the previous class is this. So, here we had used this LM335 as a temperature sensor, and then this gives you 2.73 volt at 0 degree C. So, to subtract that we had used LM336 as Zener 2.5 volt Zener, and then we have selected this resistance and designed temperature indicator. And then we also discussed about what are the errors involved in this. For example, we have discussed about what happens when the resistance drifts. Then when the resistance drifts, you will get a temperature error. Then offset voltage drifts, then you will get a temperature error. Similarly, if the Zener voltage drifts, then also you will get a temperature error. So, in this connection we also discussed what are the different types of resistors that is available. For example, if you are using a resistor, the resistance reduces a drift, but then we have if we see carefully that we have 3 different types of resistors. That is, one is carbon composition resistors, second one is metal film resistors, third one is a wire wound resistors. Carbon composition resistors gives you 300 ppm per degree C drift. Metal film resistors gives you 10 ppm, that is 10 parts per million resistance drifts per degree C, and wire wound resistor gives you from plus 300 ppm to plus 3000 ppm. So, we have discussed about these resistors, and if you want very low drift, then we have to go for metal film resistors. Of course, we have to pay higher price for that. Wire wound resistors they have only positive temperature coefficient, whereas metal film resistors and carbon composition resistors you do not know even the polarity of the drift, because some from the same batch some will have positive drift, some will have negative drift, some may have 300 ppm, some may have plus 200, some may have minus 50 ppm, anywhere from minus 300 to plus 300 ppm it will be there. So, that problem is not there with wire wound resistors, but they are bulky. Normally we use only these two unless you need high power or very low drift, then manganese resistance is good, which gives you 10 ppm per degree C drift. So, this is what we had seen in the previous class, and also we had seen what are the different types of capacitors, because resistors and capacitors play important role in electronic circuit. So, one should have a good understanding about them, how to use these resistors and capacitors effectively in a government circuit. Without that, probably your design capacity will come down by almost 50%, because normally we think that resistors and capacitors are not very important, but it is wrong. Actually, you should know more about resistance and capacitor than you know about IC, because they play a very significant role. So, if you see capacitors, we have 3 different types of capacitors. One is ceramic capacitor, then another one is electrolytic capacitor, third one is a plastic film capacitors. Now, if you look at the characteristics of these capacitors, ceramic capacitors actually the value change quite a lot with the temperature. For example, the temperature coefficient can be plus or minus 3000 ppm. Whereas, if you take a plastic film capacitors, their temperature coefficient is very low, you get 30 ppm, 25 ppm like that. Now, if you take electrolytic capacitors, they also have a large drift with temperature, but it is available in large value. For example, if I want 1 farad capacitor, I can get in electrolytic, but that is not possible with this or with this ceramic capacitor. So, ceramic capacitors are actually ceramic is used as a dielectric. Because of that, what happens normally what is done is you take the ceramic dielectric and then put 2 plates across this and then get a capacitor, and this dielectric constant of this ceramic is normally very high, that mu r is very high, it can go up to 1 lakh. Because of that, in a smaller size you will get large value capacitor. Large value means 1 microfarad up to 10 microfarad value. but net result is you get the capacitor without the inductance. So, this ceramic capacitor is the one which gives you the capacitance value with no inductance at all, almost no inductance or very less inductance. So, wherever we need capacitance with less inductance, one can go for ceramic capacitors. That is why ceramic capacitors used as a decoupling capacitors or surge suppression purpose we can use this, but they are not good for frequency determining component. For example, I should not use in oscillator circuit ceramic capacitor, because if the oscillator frequency has to be stable, and with temperature what will happen, capacitor value will change and frequency of the oscillations also will change. So, we do not use wherever very critical about the drift, we are very critical about the drift, then we do not use ceramic capacitors. But for decoupling work we can always use ceramic capacitors. Electrolytic capacitors also have a large inductance and they also drift a lot with temperature, but they are available in large value and they are unipolar. So, wherever filtering purpose, power supply filtering and power storage and so on, we use electrolytic capacitors. Then plastic film capacitor, where plastic is used as a dielectric, that you have for example that you have a plastic like metallized polyester, polycarbonate, polypropylene, there are plastics. The dielectric constant is around 7 and they are used as a dielectric material. But the problem is the dielectric constant is only 7, not like ceramic dielectric constant is very high, up to 1 lakh, like that you will get. So, because of that, to get high value, normally what is done is they take a long foil, they take a long foil and then they deposit take plastic in between and the two foils are put and the two plates are put and capacitor is made. They make a long foil and then fold it to get a capacitor. Because of that, plastic film capacitors give you very low temperature coefficient, but they will all come with the equivalent inductance. For example, we get say the plastic film capacitor that always associated with the inductor. So, they are used only where you need accurate value of capacity required and they should not drift with temperature, we use this, but then they are always associated with the inductance. So, they cannot be used for decoupling network and so on. So, this we see a little later more about these properties as we go on through the in this course, more about these capacitors and resistors we can discuss. Now, let us take next another important design, that is temperature controller. Let us assume we want to make a temperature controller and then how to go about designing that, because we had discussed earlier about temperature indicator design. Now, we design a temperature controller actually. So, let us see how to design a temperature controller. So, in this lecture basically we will design what is called on off controller. I will talk about these different types of controllers little later. So, let us take here on off controller. Just the name had come mainly because we are going to switch on or off and then that is how our controller going to work. So, we will talk more about on off controller, periodic controller and so on little later. So, let us see how to design a temperature controller. Now, for this we need a temperature indicator first, because if we want to control something, all that we need is we have to sense the temperature and then compare it with the reference and then control the heater. So, we have 3 parts in any control system, that basically we have one block for temperature sensing, for example sensing. In this case it is temperature. So, I have to sense the temperature, then after sensing the sensor gives me this is the input temperature input, and this gives you the electrical output. So, in this case we are sensing the temperature and corresponding to the temperature we will get a output voltage. Now, this is so we need a sensing part first, then the sensor voltage must be compared with the reference. So, we will have a comparator and then wherein we will have reference is given. So, if I want to sense the say if I want to stabilize at 70 degree, then I give for example corresponding to 70 degree voltage. For example, I assume that I am getting here 10 millivolt per degree C. That means if it is a 70 degree, I will get 0.7 volt. 0.7 volt, then I give reference also 0.7 volt. So, the temperature sensing first part, then the second part is comparator. You have to compare the compare with the reference, whatever temperature you want to stabilize, that that corresponding to that voltage to be compared with the measured voltage. Then you have to have a heater drive or motor drive or whatever it is. So, you need a drive. So, any control system needs these three parts, that is drive, then comparator and then sensing. Now, in this case let us take LM335 as a temperature sensor, and then we take one op amp, for example our friend 741 we take as a comparator, and then here we want control temperature. So, the drive will be heater drive. So, we will have a heater that has to be driven. So, this is what we are going to design in this lecture. So, let us see next what we do with this. Now, what I do is first I should sense the temperature. So, for example, in this case assume I want to maintain the temperature of bath, and you have water in this. Assume I want to maintain the temperature of this water at say 70 degree C. So, what I do is I will put the sensor here, which is LM335. So, we have a sensor that is dipped into this. It measures the temperature of I put LM335 here. This is a temperature sensor which we had discussed earlier. So, I take this, then I have to bias this because I know to send 1 milliampere current through this. So, I give plus 15 volt to this, then voltage at this point gives me temperature of this water. For example, if it is 25 degree C, I know that I will get 2.73 plus 0.25 because it gives you 0 degree C 2.73 volt, at 25 degree C it gives me 0.25 volt. So, you will get 2.98 volt you will get at room temperature. So, this is grounded and then I bias at this. So, it will give me 2.98 volt at this point. So, assume that I want to maintain this at 70 degree. If I want to maintain 70 degree, then I have to have a heater. So, I will put a heater inside. So, I got a heater here. So, I should if the temperature is low, for example, I want 70 degree. Now, in the morning if I switch on, the temperature is the temperature of the water is 25 degree C. So, I want to take it 70 degree means I have to apply a voltage to this heater. So, that this dissipates heat and then the temperature of this goes up. Once it reaches 70 degree, then I switch off the heater, and then again because of the radiation here, then the temperature will come down. Once it comes to 69, I will again switch on this. So, again reaches 70, I will switch off. So, by monitoring this temperature and correctly switching on off this heater, I can maintain this. Now, this is to be done electronically. So, what I do is I will connect this to the ground, then I take this heater, then I want to switch on the heater means I have to do it through a transistor. So, I assume this is a high power circuit. So, I put a Darlington pair, then assume this is a plus 15 volt. So, I connect the heater to this. So, if this plus 15 volt and assume that I, for example, I give here 10 volt base, if I give 10 volt, then I know that at the base I will get 9.4 volt and here I will get 8.8 volt. So, now the if you see this, the voltage actually goes here and this 8.8 volt is applied to the heater. Now, the temperature will this will be heating up and the temperature will be rising. So, here we are applied 10 volt. If I can apply up to 15 volt, I can't go more than 15 here because our supply itself only 15, and this is Darlington pair. this is used to boost the current, because the heater current, say for example, if it is say 5 ampere, then we know that the base current of this will be beta times less, and then this base current will be even beta times lesser than this. So, what happens if it is 5 ampere, if the beta of this is 50, then this current will be 100 milliampere. If this beta is 100, then this base current will be 1 milliampere. So, here 1 milliampere current will be flowing, whereas here 5 ampere current will be flowing. So, to boost the beta only we have done this Darlington pair arrangement. So, the advantage is now I need only very small base current. Suppose if I apply a small base current, that is multiplied by the beta times, I current comes. So, my controlling device which is going to be operational amplifier here need not give high current, that is why this arrangement is made to drive the heater. So, now let us continue our discussion. Now, I remove this 10 volt. Now, I give this one from my control circuitry. So, what I do is I know the temperature here. So, I have to give, for example, the simplest controller could be this. I can have plus minus op amp, that I can give it to this, fine. Then the temperature I give to here, and then plus I had give a reference. So, a reference can be from a Zener. For example, I can have a Zener diode, say for example 2.5 volt Zener is there, LM336, because you should familiar with some of the device that is available in the market. This is a very important thing as a designer. One should know what are the components available, how much it costs, so that one can have a correct choice of components, because the price is an important factor. You should not end up in selecting a device which is costly, which cannot be used in the practical world eventually. So, one should aware of a few components at least, so that the design strain will be very less. Now, if I want at 70 degree, I know that this will give me 2.73 plus 0.5, that gives me 3.23 volts. So, at 70 degree it will give me 3.23 volt, at room temperature it will give me 2.98. So, that means when the temperature is lower than 70 degree, it should heat up. So, what I do is I will put on potentiometer here and connect this to here. I keep this one at 3.23 volt. I adjust the potentiometer such that I get 3.23 volt to this input, to the plus input. Now, that basic temperature controller is now complete. If we see how this works, see we have sensed the temperature here. For example, in the morning when you come and switch on, and the water will be at room temperature. So, room temperature corresponds to say roughly 25 degree C. If it is 25 degree C, then obviously this will give me 2.98 volt will be there at this point. We have set this one at 3.23 volt. That means the plus is higher and minus is lower, and this op amp is supplied with the plus 15 minus 15 supply, plus 15 volt and minus 15 volt supply is given to this op amp. Now, if you see, this is sitting at 3.23, in the morning this is sitting at 2.98, that is corresponding to 25 degree C. That means this is higher, so output automatically goes to plus 15. Once it goes to plus 15, this comes to 14.4, this comes to 13.8. That means this goes to plus 15 and this comes to 14.4, and then this jumps to 13.8. That means now heater is getting 13.8 volt and started heating up. As it heats up, the water temperature goes up, and then this temperature also goes up, and then this voltage also goes up. So, slowly the temperature at this point will be voltage at this point. So, slowly voltage at this point will be rising. The voltage at this point rising, then basically what happens, if you see the difference between these two is keep decreasing, but we know in any op amp the difference between these two multiplied with the open loop gain is the output. whether it is closed loop or open loop, this is always true. So, the difference between plus and minus multiplied by open loop gain is what is appearing at the output of the op amp. Now, this is 3.23, and if this is less than 3.23, even 1 millivolt less, say even 3.22, say just 10 millivolt away, then 10 millivolt into open loop gain, which is very high, which is around 50,000, the automatically output becomes plus 15, because it can't go more than plus 15. So, it is stuck with plus 15 and it is heating up. But the moment it comes to 3.23, because the temperature is rising, and the moment it comes to 3.23, then the difference becomes 0 and then output becomes 0, or even if it goes slightly more than 3.23, then output shifts to minus 15. Once minus 15 comes, we should not apply minus 15 to this one. So, to block the minus 15, I put on diode. So, when minus 15 comes, no voltage comes, when plus is there, the plus voltage goes, the diode conducts, and except that 0.6 loss, which we are not worried, then the voltage comes. And when this goes little more than, if this is 3.23, when it goes little more than 3.23, output become minus, and the no voltage comes here, and the no voltage comes here, and the heater goes off. Once heater goes off, then because of radiation from the beaker, then what happens, the temperature start coming down, and once temperature comes down, then this voltage also will start coming down, and if this goes say below 3.23, again this will go plus 15, and then 14.4, and then you will see 13.2 here, and the heater heats up again, and again temperature will go up. Once temperature again goes, then once it goes 3.23, more than 3.23, again it will turn minus and it will go off. So, like that it will keep going on off, and then maintain this around 70 degree C, not exactly 70 degree, it will be maintaining little more than 70, and then it will come down little below 70, like that it will be doing, and then frequently it will be switching on and off, and then maintaining this temperature. In fact, this is what we do in real life. For example, if the controller is not there, if without that if I have to do, then what we do is we will put a thermometer here, and then if the temperature is low, I will switch on the heater. Once I reach the set temperature, I will switch off. That same thing is done by the electronic controller here by switching on off. So, this is a famous temperature controller. In fact, most of them even today it is used. It is very easy to construct, but only problem is that if you want 70 degree, it will be going up and down 70. Say it will, once switch on, it will go little above 70, and then slowly it will come down, then come to 69. So, depending on the system, there will be overshoot and undershoot. If the system is fast, the overshoot and undershoot will be small, otherwise overshoot and undershoot will be more. Other than that, it is a good and famous controller, age old controller, and works beautifully, there is no problem, but except that you have a small temperature fluctuation. And also if you see in this mode that this will be frequently going on off, and many people even use instead of this various other possible drives, which I will explain you a little later. So, if we see this one, there it will have a on off feature going very frequently. We can reduce this number of times going on off by introducing a hysteresis. That we can do like this. What I can do is that I will show you in the next circuit. So, now I will draw a little simpler circuit to this. So, all that need is that I have this controller minus. So, to this I have my reference temperature, which is to be set, that I have done it here, and then minus. So, this gets the temperature information from the, this is sensor. So, this is given to this, and then the output, to block the minus we have done this, then we have driven this and then the heater. Of course, this and this are actually mechanically coupled, this and this mechanically coupled. Now, our worry was that frequently it is going on off, so we want to avoid that. Now, I can do that by adding a small hysteresis. For example, when it is on, it should not go up. So, I can take this, I can add one resistance to this. Now, whatever voltage is here only it is coming here, I can add one more resistance here. This will add a hysteresis, so called hysteresis, and then this will avoid frequent switching on off on off. So, what is really happening is that when the initially when the temperature is high, that you will have this voltage is plus 15 and part of the voltage is coming here. So, if I am setting at 0.7 here, say if this is at 0.7, assume this is at 0.7 volt, that is what you have set here by adjusting this. So, if I make it 0.7 here, this 0.7 partly are come from here as well as from here. Assume this contribution is small, that assume that this contribution is small. So, you have a contribution from here and you have a contribution from here. Assume the contribution from here at this point is only 20 millivolt. 30 millivolt is contribution from output. Remaining 680 millivolt is contributed by the potentiometer. I will show you how to compute that. So, we have taken here because of this the contribution is at this point is 0.6 that is 680 millivolt. From here because of the output some voltage here, because this voltage and the this voltage and this voltage both are added here and that is what you got 0.7. Out of 0.7, 20 millivolt had come from here. Now, what happens is when initially when the room temperature is low, that is when the oven temperature is low, then this will be high and you got 0.7 here, but moment when it is heating, then after some time you find that this voltage is going up. Once it comes more than 0.7, then this will turn to minus 15 volt. Now, once minus 15 volt comes, this contribution becomes minus, that means this fellow will drop to 600, this is 680 millivolt is coming from here and 20 millivolt was coming from here. Now, this will 680 minus 20 it become 660 millivolt at this point. So, when it is plus it was 0.7, when it is minus 15 it becomes 0.660, that is 660 millivolt. Now, what happens, since it is set at 660, only when this point goes 660 millivolt, the output will change again to positive. That means, what is happening is once actually if I take this, once it is minus 15, that is if this is minus 15 volt, then this voltage is 660 millivolt. When it is plus 15 millivolt, when it is plus 15 volt, this is 700 millivolt. When it is 0, it will be 680 millivolt. That means, once it turns minus 15, this voltage is reduced 660. That means, again it will turn on only when this only when the temperature here goes below 660, because now when it is minus 15, this is sitting at 660 millivolt and the heater is off. There is minus heating, heater is off, so it is cooling down. Once it cools down 4 degree, that is 660 millivolt, then the output again will go high. Once it goes high, this fellow shift to 700, then again it will go off only when this fellow reaches 70 degree. That means, you will see it switches on at 66 degree and switches off at 70 degree. So, you got a 4 degree gap. So, you will not get a frequent going on off. So, now we are given a 4 degree hysteresis by adding 20 millivolt at this point due to this, we got a 4 degree hysteresis. So, we can set whatever hysteresis we want. For example, if I select a resistance such that only 10 millivolt is added here, then I will get 2 degree, because 10 millivolt corresponds to 10 millivolt at this point corresponds to 1 degree C error. So, 20 millivolt change here will correspond 2 degree error. So, you will have hysteresis of 20 millivolt here and temperature swing of 2° here. So, it will switch on and off only once in 2° change, that will reduce the frequent switching on off. So, this is called addition of a hysteresis. So, one can add a hysteresis by suitably selecting this resistance and this resistance. Now, we have to talk about this more. We will come to that a little later. We can reduce this drift by suitably selecting this. I will show you the calculation. Right now, do not get worried too much about this calculation. All that matters is when it is plus 15, the voltage is added. When it is minus 15, this voltage is decreased. So, once the voltage decreases, this has to go to much lower temperature to make it come on again. So, by this way on off control can be made by adding a hysteresis which will avoid frequent switch on and off. And this frequent switch on and off is okay if this user transistor, because we need to avoid frequent switch on and off if we are not using transistor. Then what is the option that we have if we are not using the transistor, let us switch on and off the heater. Now, that I will show you in the next circuit, that what I do is I need not use only transistor to make it on off. I can use it there are many other options I have. For example, I can do this. So, I redraw the circuit again. For example, this is a sensor. I give plus 15 volt to bias this, then I will have reference voltage from Zener. So, they have here plus 15, and then I have a set value, I can get it through potentiometer. Then I have a comparator here. So, I compare this minus and plus. Right now, we need not worry about the hysteresis. Okay, then I put on diode. Then instead of giving a Darlington pair and then switching on and off the heater directly, I can do this. For example, I can give to a transistor, then I put a relay, this for example plus 15 volt, then I put on diode, then I show you what I explain you what is a relay. Then this relay can be connected to the supply and then the heater. This is the heater which is connected to the oven, and then for example, if I want to show that in the this thing, I can show it like this. I can have a heater here, then the heater wire can go here and come back. This voltage now, if I take this voltage, okay. So, whatever voltage are given, that is supplied here when this is on. When this is off, whatever voltage is given here, when the contact is open, this voltage will not appear here. When the contact is closed, this voltage will appear on the heater. So, this is actually the crux of the issue is that this relay, the relay and this diode. So, this relay, this kind of arrangement we use very frequently. We will know the reason for this, called the relay. Now, the what is the relay actually? The relay is actually if we take this one, I take a bobbin and wind a few turns of wire, then I pass a current through this. Once I pass a current, that magnetic field is set up, and then you will have a magnetic field produced in this. And what can be done is that I can use this magnetic field to pull some iron piece, and that can made to make a contact here. Suppose if there is no voltage here, there is no current, and then for example, I can have a metallic strip, and then I can attach it to this. So, whenever this is the core of this. So, whenever current is flowing, then this get magnetized and this fellow will pull this, and when no current is flowing, and this will not magnetize and it will not pull. So, what they do is they will attach a spring to this and fix it to this. So, whenever when current is flowing through this, the magnetic field is set up and that will attract this, and then when no current is flowing, that will release this. So, like this we can make a mechanical movement, and then to this you can attach to this you can attach with the insulation various other contacts that you need, like this. Like for example, if this is there, it will make contact, otherwise it will not make contact. You can do this kind of arrangement can be made. So, whenever current is flowing, there will be a magnetic field and that will be pulling this, and that will make this to close. When no current is flowing, then the spring will pull it back and this contact will open up. So, we have just got a free mechanical contact which opens and closes depending upon the current flowing in this coil. So, that is the coil that we had shown here. So, this is the coil of the relay. So, whenever current is flowing through that, eventually it closes, and when no current is flowing, that this opens up. So, other way around, if I apply a voltage here, then the transistor will conduct and current will flow through this, that will make the contact to close, and then the current will flow and the heater will be getting the power and this will be started heating. If I remove the voltage this to 0, then no current will flow through this, and then the relay contact will open and then no current will flow, this, that is the heater is off. So, we can make the heater voltage to go on off using the relay also instead of a transistor. Now, the relay has some advantage. The advantage is that I can apply even 300 volt, or it can be AC or DC, anything, or it can give 5 ampere, 10 ampere or 230 volt or 440 volt, whatever we want we can apply. That freedom you get if you are using a relay. So, for high power or it is a AC current, this is good, one need not struggle with the transformer. One need not struggle with the transistor, because transistor has a voltage rating. If you use for example 2N3055 as a transistor, then it can withstand only 70 volt. Above 70 volt the transistor fails. So, that kind of limitation is not there if I use a relay. So, in that case per high power oven, for example, if it is a 1000 watt oven, then what I can do is I can put here instead of this, I can put AC of 230 volt, can connect, and then when it is on, 5 ampere current will be flowing and the heater will be on, and then when I put off this 0, the no current will be flowing and this will be open and the heater will go off. So, it is easier to handle AC or very high power like this if using a relay. But the relay contact disadvantage that it is a very slow, it can't be switched on and off very frequently. For example, switch on only the manifold set up, and mechanically it has to pull, and then when you off, then the spring has to pull back. The normal on off time itself will be around 50 millisecond. So, normally we do not try to switch on more than 10 times a second, and also when you switch on every time on and off, if you do, you will see a spark coming here, and the contact here actually goes off every time when you on off, and also it produces it radiates a noise outside to the space. So, relay has the drawbacks that after several thousands operations you will find the contact here is not good. So, the relay they specify what is the number of on off that you can carry out for a relay. For example, there are relays which can withstand 1 lakh operations. There are relays which can withstand only 1 lakh operations. After say if it is specified as 1 million operations, after 10 lakh times, then the contact goes off, and even when the current flows through this, it may not make proper contact and current may not be going fully. So, this problem will be there in the relay. Also, this produces a lot of radiated electromagnetic noise whenever the contact open and break. So, that problem also there. Nevertheless, this is capable of carrying high current AC as well as DC. So, this is still used extensively in the industry. For power, for example, this need not be even a heater, this can be even a motor, wherein if I am using a position control. If I am using a position control, then I have to switch on the motor when it reaches if it is below the desired position, and when it reaches the actual position I will switch off. So, I have to do this using relay, it can be easily done rather than driving the motor which has its own complications. Of course, the speed what you get through the relay operation is less and it is limited, and also accept the noise. That is why the relay is used. So, this is a temperature controller using a relay. For example, if it is oven temperature to be controlled, then all that I do is that I will put the sensor, that is this inside this, that is all. physically I will put it here. So that the temperature of this is sensed and then accordingly it switches on. Suppose the temperature is high, then output goes in this point output goes minus. Once minus goes, it will not conduct, and then this current flowing through that will be stopped and this opens up. And you may wonder what is this I have done here, I have put on diode here. If I do not put this diode, then what happens is invariably you find that this transistor goes bad. Whenever I switch off, then this transistor goes bad. To save that only, we added this diode here across this coil. Actually, if you closely look at what is happening at the coil actually you have a wire and wound on this, and the coil has appreciable resistance. So actually if you see in the actual this thing, if I draw the equivalent circuit relay, it is nothing but a resistance and a coil equivalent, and then we have this diode connected here. So when you switch on the transistor, when you get plus 15, then current flows here, the base current beta times that current flows here. So current flows through this, and as the current flows through this, then the coil the current magnetic field set up in the coil, and then eventually the current that is finally flowing through this is limited by the resistance. For example, if it is a 100 ohm resistance, assume this is a 100 ohm resistance, then the current that is, we take this as 100 ohms, then maximum current that it can go through this will be 15 volt divided by 100, that is 150 milliamps. So what may happen, the current that can flow will be only 150 milliampere current only, because we have taken this coil is 100 ohms. So once you switch on, the current will slowly rise. How much time rise? Because the inductor current rises only by this, I is equal to V by L into T. Probably it will take few milliseconds depending upon the inductance value to reach the 150 milliampere, and current cannot go more than 150 milliampere, because once 150 milliampere flows, that you get 15 volt, all 15 volt across this, and there is no more volt to drive the inductor. So at 150 milliampere current will saturate, and that time definitely the coil would have pulled the contacts, so no problem. But then the problem comes, okay, I apply the voltage and 150 milliampere flows and the contact is closed and heater is on, that is fine. Then the temperature goes up. Once the temperature goes more than the set value, output turns minus. Once minus 15 comes, then the base voltage is removed and the transistor anymore cannot conduct anymore. The transistor not conducting, then that means we switch off the transistor. Once you switch off the transistor, at that time before switching off, the 150 milliampere current was flowing through this coil. If at this point if I cut, then whatever current that was coming from here, that not able to find a path here. And if I do not put this diode, then what happens, that you are trying to stop the current through the inductor abruptly, because transistor switches off, for example in 1 microsecond time it takes to switch off, then 100 milliampere current that is flowing, it will be stopped in 1 microsecond time. So the current flowing through the inductor you are trying to stop in 1 microsecond time. So the voltage developed across the inductor is the L into di by dt is the voltage developed across the inductor. So if I see this little detail, so voltage across the inductor goes to L into di by dt, that is the voltage level. That means if I try to stop, so if I switch off the transistor, then the current stopped in 1 microsecond, that 150 milliampere current stopped in 1 microsecond. That means your di is 150 milliampere, and the time what taken is 1 microsecond. So, if then if we take this LdI by dt, then voltage induced on the inductor will be very huge, because you stopping the current through the inductor abruptly, that is in 1 microsecond, the 150 milliampere current is stopped. So, if I take for example L as 1 Henry, then 150 milliampere is stopped, then dI is 150, the time is 1 microsecond, then you will get 150,000 volt developing across the inductor. That is very high. So, what will happen if you try to stop, the voltage at this point goes trying to rise very high value, then the transistor cannot withstand that voltage, then transistor goes bad. So, you should not the lesson is that you should not stop the current that is flowing through the inductor abruptly, but eventually we have to switch off, then only the heater will go off. To solve this problem only, we added this diode. So, now once you switch off, whatever current that is coming from here, that actually the voltage once the current stops here, the voltage trying to rise, but then once the voltage, because we know that this chap is sitting at plus 15 volt, this is sitting at plus 15 volt. If this goes, because once you stop, the current flowing through this is start reducing, and voltage at this point start rising because of LdI by dt. Then once the voltage goes more than 15, this started conducting. So, this is 15, this can go only above go only up to 15.6. That means the voltage at this point cannot go more than 15.6, and then transistor will not go bad, because this is made to work much higher than 15 volt. So, what is happening is current whatever is coming here, it goes like this, and after a few circulations it will dissipate as a heat in this resistance, and all the energy stored in the inductor dissipated, but voltage at this point never goes more than 15.6. So, the transistor not destroyed, that is protected. So, you will see this kind of diode protection at many places wherever inductor is there, to dissipate the energy stored in the inductor, this is used, otherwise this transistor would have gone bad. So, this is a must to use the inductor here. So, using a relay also we can make on off controller. Now, there are very many ways that we can do. For example, if the heater voltage is, we had shown two things how to control the heater. One is through relay, that is one case, if I show the output. So, in one case what I had done was the comparator output was there. So, I had given through Darlington pair. Here plus 15, and the second circuit I had shown that I have this, then diode, then I switched on off, I had put this, I put a relay, and then this plus 15, the second way of doing. There is yet another way of doing. For example, I can also do like this. I can put the heater here, or even I can put high current, I can even go for a okay, I can put this, it can go even 100 volt. Of course, I had select a transistor for 100 volt. So, this will be a heater in this case, or I can even do in it another way. I can do in a, see this itself I can modify as a, for very high current I can do this. This I can give it to the comparator here. So, you see there are different ways of switching, this is actually a direct drive, this is direct drive, this is through relay, the actual power is going through the contact here, and this is actually when the voltage is when the voltage goes high and this transistor conducts and full heater voltage applied, because here we can go more than 15 volt, whereas in this case the heater voltage will not go more than 15 volt, because this can go only up to 15 and this will be 14.4, 13.8. So, roughly around 13-14 volt only you can get on the heater, not more than that. So, this is not possible. So, if you compare this and this, here heater voltage can be very high. Here this case the heater voltage can be even higher, or AC as well as DC. This only DC possible, but can go higher voltage, whereas if you want very high power I can do this, that is I can put this or put the diode to block the negative. So, I can use the Darlington with the ground at 1. So, this can be even higher voltage, high power. So, I can use this. So, you can do it in very many different ways depending upon your application and the heater requirement. In this case, this is the heater. It can be even 5 ampere, because we have put a Darlington, and if you need high power it can go. You have even transistor up to 1000 volt, there is no problem, it can apply heater voltage. Of course, you can't use a AC voltage in this case. If it is AC voltage, it is not difficult, you can rectify into DC and give this. But then one more thing you have to watch here, that in all these cases we had used this resistance, these two resistors to switch on and off the transistor, which I have not explained. So, if I go back and see why I used this, for example, even here I had used this resistors. Similarly, if you see this, here I had used this resistor. So, all these places we had used. This is to make it on off actually, to know. For example, why did I use this? Because I want to make this transistor to go on. So, at that time the voltage applied here is plus 15, if it is 15 I know 14.4 will come. So, if I want to switch on, definitely I should not connect like this, the output whatever is coming, that you have the diode, then I do not put this diode, I do this, for example I do this and connect the heater here, say this is 100 volt. If I do this, for example this is your comparator, if I do this, this transistors will go, but you should not do like this, that is you have not put any resistance here. Here you see, if you compare this and this, we have put a series resistance and then you also put one resistance to ground. Here we have not done this. If I do like this, actually this transistor goes bad. Now, you may wonder why it is happening. This is because, for example, if I give this tends to plus 15, we know that this will go to 14.4 volt. If this goes to 14.4 volt and then this has to go to 13.8 and this is already grounded. So, this point is ground and this is sitting at 13.8. If we apply 13.8 volt between base and emitter, this is a base and volt 13.8, then the transistor forward current will be so high and the transistor will get destroyed, because above 0.6 you normally do not see any across base emitter voltage. 0.7 is itself is so huge. So, you do not see normally more than 0.7 or 0.8 across any transistor in the forward condition in between base and emitter. So, you cannot apply 13.8, that will definitely destroy this. That is why we have to add we do not use this. So, do not do this. So, if you want drive, then put a Darlington, no problem, connect this to ground, then you drop the voltage across this resistance, that is what you have to do. So, this resistance is a must, you have to have this resistance. Without this resistance, you should not connect the output directly to the transistor. If you connect, the transistor goes bad. Now, what happens because of this resistance? If I connect this resistance, now this point will come to 14.4 and we know that this cannot be more than 0.6. So, voltage across this only 0.6, voltage across 0.6, that means this will sit at 1.2 volt maximum, not more than that, automatically will come. So, the difference across this, if you see this voltage across this is 14.4 minus 1.2, that is actually 13.2. So, the extra 13.42 volt will drop across this. Other way around, the current that is flowing here develops a voltage across this, and then this voltage automatically comes to 0.2. Now, for example, if I put here say if across this is 13.2 volt. So, if I put say 1k, then or 2.2k I put, assume that I put 2k, then the current through this will be to get 13.2 volt, 13.2 volt divided by 2k, that will be 6.6 milliamps. So, you will find if I put here 2k, you will get 6.6 milliampere going here, and you will find this point is sitting at 1.2 volt, because this is sitting at 0, this is sitting at 1.2, this is sitting 14.4, and you will see the current of 6.6 milliampere is flowing through this. If I put 1k, automatically 13.2 milliampere current will flow. So, depending upon the requirement, current requirement, I can select this resistance value. Now, if I select 2k, then you will find 6.6 milliampere current is flowing through this. If 6.6 milliampere flows through this, we know this transistor as a HFE, and if it is 100, then I know that the current here will be 100 times more, the emitter current will be 100 times more than the base current. So, per 6.6 milliampere here, I know that this current can be as much as 6.6 into 100 milliampere, 100 times. So, that will be 660 milliampere current. You will find 660 milliampere current is flowing here, and then that will be multiplied again further by this transistor. This transistor carries the bulk of the huge current, because this will be again multiplied by beta of this. This big transistor have lower beta. For example, 3055 if I take, the beta is only 20. Smaller transistor have higher beta, that can be even 100. So, this if I take this, so if I take this transistor beta as 100, then 20, so I take this as 20 is beta, then 660 milliampere multiplied by 20 will give me 13 ampere current can go. If 13 ampere current cannot go and limited by the resistance, then whatever current that can flow, it will flow. So, up to 13 ampere current can go through this if I use this. So, transistor will not get destroyed if I put this resistance. So, if I want more current, if I want say 20 ampere current through this, if I select 20 ampere current, then I should reduce this resistance such that I will get 20 ampere current through this. So, depending upon the current requirement, I can select this. So, the of course, if you select lower value, then large current can flow. If that much current is not flowing, no harm, only thing is effective beta comes down, that is all. So, no issue if you select a lower value. Of course, that lower value, the higher current will flow, and that must be supplied by this op amp, and if that is not able to supply, then the voltage will decrease. So, obviously you should see both, no need to drive too much current excessively. So, select this resistance such that suppose if it is 100 volt and if it is 100 ohm resistance, then you need only 1 ampere current through this. If 1 ampere current through this and the beta is 20, then I know that 50 milliampere current will require at the base. So, 50 milliampere current here will drive 1 ampere current here, because beta is 20. If 50 milliampere current here, then if beta is 100, then I will have 0.5 milliampere current only required here. So, to get 0.5 milliampere and I need 13 volt drop, then I need to have 26k, say 27k resistance will be enough. So, that is how this resistance value to be selected. Of course, we need one more resistance in a real case, that is one resistance we put here to ground. This is, when it is going off, there is a capacitance here, the storage charge is there, and that to be leaked through this. So, that depends upon how fast you want to. This resistance selection of this we will discuss in the next class.